you to my lecture today. Of course, I sent a message earlier that today I was going to conduct today's lecture online. I first want to confirm if everyone is hearing me clearly and if you're also seeing my lecture slide.
We're able to hear you and we're able to see the slides.
Okay, thank you so much. Thank you for confirming all of that. For now, we started the function of random variables. And of course, this is the last chapter that we're actually going to be focusing on in this semester. Of course, you've been introduced to this, and of course, you know the essence of figuring out the function of a random variable. I'll first have a kind of recap before I go into today's lecture. Actually, we have a variable x that follow a particular distribution. The variable x could be discrete, could be continuous. And we now define a new variable y, and you know what, the new variable is a function of the old variable. And what we want to do now is to figure out the distribution of the new variable, putting into consideration the old variable. And of course, I unveil some method of achieving that. Number one was the method of distribution function. I also walk you through the method of moment generating function. We started the method of transformation yesterday that I'm actually going to continue. Of course, 100% of what we want to do today is basically to see how the method of transformation work. So in the method of transformation, I'm actually going to walk you through one variable situation and two variable situation. And what is the significance of all of that in real life, practical situation? Of course, I can confirm to you that the application of function of random variable actually spread, you know, widely from medicine to engineering to economics to business and so on like that. Okay, so I need you to pay attention to what I'm displaying now. I basically want to show you how this particular method that I call the method of transformation work, where we're dealing with discrete random variable, okay, and where we are working with one variable. Take a look at, if you, give me 1 second. If you take a look at this guy now, you basically, let me just see if I'll be able to, okay, give me 1 second. Let me see if I can make use of my pen now. Okay, so now if you take a look at this particular guy, okay, that's a discrete, right? That's a discrete. And of course, you know, it's one variable, x, and we're seeking to get the probability distribution of a new variable y, and that's a function of x. Now, let me tell you this, that of the discrete is very, very easy. If you want to work out on the, you know, if you want to use the method of transformation, all what you're just going to do is to obtain the inverse. You're going to obtain the inverse of this. You know, obtaining the inverse is like solving for x. Okay, when you solve for x, this is what you're going to get. Okay, and you know what you're going to do? Anywhere you now come back into this particular function here, Anywhere you see x, you're going to plug in square root of y. Okay, that was what led to this. Okay, you're going to plug in the square root of y, and you need to also define the state space for y. Initially the state space for x was 1, 2, 3, right? And now am I going to get the state space for y? I'm actually going to make use of this relationship. When I plug in 1 here, 1 squared is going to be 1. Okay, 2 squared is going to be 4. 3 squared is going to be 9. Do you know we're already done? Is there any question on how to do one-to-one, transformation for discrete random variable? Is there any question on this? That's super easy, right? Is there any question? If you really understand what I just explained now, I need you to say yes, or you comment yes, or you give me a thumbs up if you really understand my explanation. Okay, I always say one person, okay, I think I'm saying, but you know what, if you don't really understand, please let me know. So doing one-to-one with method of transformation for discrete is very, very easy. Very, very easy. Okay, so that's what I have. I'm gonna go to the next example. Now, I want to talk about two variable situation. In a two variable situation, of course, you're basically going to be provided with a joint for x1 and x2, because you got a joint, okay, for x1 and x2, okay. And when you actually get a joint, okay, for x1 and x2, okay, then they define a new variable y1. It's a function of x1, x2, and the new variable y2 is a function of x1, x2. Of course, in this situation now, you actually considering two variable situation where you want to go from x1, x2 to y1, y2. Okay. And you know what? In that kind of situation, you also need the inverse, just like the way we find the inverse the other time. Okay, like this guy now, getting the inverse, I got x1, x1 is going to be a function of y1, y2, and x2 is also going to be a function of y1, y2. And from f of x1, x2, if I want to get another function for the two new variables, or what I'm just going to do, wherever I see x1 here, I'm actually going to plug in, this particular one. That's what you see in this. And wherever I see x2, I'm going to plug in this. I'm done for discrete. If it's for discrete, it's going to be super easy, whether for one variable or two variable, you get what I mean. So it's going to be super easy. Now, what I'm going to do now, I'm basically going to make use of, going to go into an example. Okay, want to look at the example now. We're talking with discrete random variable, and of course, we got joint, and we basically take a look at this. Let x1, x2 be two independent random variables having point z distribution with parameter mu1, mu2. Find the distribution of the random variable. Take a look at this guy now. You want to find the distribution of the random variable, which is going to be x1 plus x2. You remember yesterday, we did, stuff like this, we approached that using the method of moment generating function. Okay, so the moment I know the moment generating function of Poisson distribution, okay, so I know the moment generating function of Poisson distribution, and or what I can do, I can just apply what I call the moment. If I want to get the moment generating function of y1, it's just going to be the product of the respective moment generating function. From there, I'm going to figure out what the distribution is going to be. I'm just trying to recall the method of moment generating function. But right now, we're not using moment generating function. We basically want to use a method of transformation. Okay, now we want to use method of transformation because of the fact that you are told here, okay, that the two variables are independent. Okay, the two variables are independent. You can, four of us get a joint. Okay, so they are independent. Of course, the joint is basically going to be the products of the f of x1 and f of x2. So what I'm trying to tell you now, this is the Poisson for x1 and this is the Poisson for x2. Okay, don't forget the x1 follow Poisson with parameter mu1 and x2 follow Poisson with parameter mu2. Of course, we're going to multiply them. By the time you simplify this is what you're going to have. This guy now become a joint PMF. That's a joint PMF. Okay. That's a joint PMF. Right here is more or less like to give a state space, X1 and a state space for X2. Okay. That's what we mean. Okay. But let me tell you this, you know, there's something I want you to take notes. You actually want to go from x1 x2 to y1. That is not possible. Okay, we can have 1 to 1, we can add 2 to 2, 3 to 3. We can never have 2 to 1. Okay, so what you're going to do, we can actually create an artificial variable y2, and that very y2 is basically going to be equal to one of the old variable, so that we'll be able to have 2 to 2. Maybe just like let's say they invite a couple to a party. They actually want couple to come to the party, and maybe my wife is not around. Okay, my wife is not around and I want to go to the party. Okay, you know what I can do? I can ask one of my daughter to go with me. Okay, so if my daughter go with me to the party, okay, it's going to act as my wife in the party. There I mean. But you know what? By the time we leave the party, my daughter is no longer my wife. So what I'm trying to say here, we actually created an artificial variable, okay, in order for us to be able to use the method of transformation, because we can only go from 2 to 2, we can go from 2 to 1. But in the end, we actually going to marginalize, whatever artificial variable that we introduce. We have a way to actually marginalize that, just the same way when we get home from the party, then I'm going to say, my daughter, thank you. You are no longer my wife now. You acted like my wife at the party, but right now you are no longer. Okay, so because of that, I'm going to get the inverse of this guy that I introduced, where what is x2 here? Okay, the x2 is basically y2, right? And here I'm actually going to solve for x1. Okay, solving for x1 is going to be y1 minus x2, which is, and what is your x2, y2? So you're going to have this. Okay, so these very two now become inverses. Okay, become inverses. With the method of transformation, you basically need, okay, to figure out the inverses. Okay, now we got these inverses now. Okay, now getting the inverses now, don't forget this guy here is actually the joint for the old variable. Okay, or what I'm just going to do here now, just to plug in, what is the expression for x1? Plug that in here. The expression for x2, plug that in here. So when then you plug all this guy in, oh my God, you're actually having a new joint distribution now, which is a g of y1, y2. You have completely eliminated the old variables x1 and x2. Take a look at that. Okay, so we got G1, Y1, GY2, but you know what we're looking for, right? We are seeking to get the distribution for what? For Y1, okay? And based on the knowledge in class, what I'm seeking for is actually the distribution of Y1, then I'm actually what I'm going to do is basically to sum, I'm actually going to sum this guy here, which I call the G, okay, of, Y1, okay, the G of Y1 and Y2. I'm actually going to sum that with the respect to the variable I'm not interested in. Oh my God, which variable am I not interested in? Of course, the one that I actually created. It's just like, okay, we are done with the party now. My daughter, okay, you got to go. You are no longer going to have as my wife. Okay, that is what we mean. So that's what we want to do here now. Can you somebody confirm again if you are still hearing me clearly?
Yep, we can hear you.
Okay, thank you so much. Now, the next thing I'm going to do now, oh my God, that's exactly what I'm doing here. I want to get my dad, we're actually going to sum, from Y2, to Y1. Don't forget, that's what we actually going to do. By the time you do that, then this is what you're going to have. Okay. That is what you're doing now, you're doing now. So in the end, you're basically going to have this guy. And when you have this guy, if you take a look at this guy, it is same thing as a combinatorial analysis. Take a look at that. You see that guy now, right? Okay, so when you take a look at what I have here, give me 1 second. When you actually take a look at this guy now, when you take a look at this guy now, okay, that guy is the same as this guy according to the law. Okay, it's a binomial expansion. You remember binomial expansion. Don't forget this guy here is still this guy here, right? Okay, so automatically this guy here is this because we're using the idea of binomial expansion. Oh my God, this is the distribution I'm actually seeking for. My h of y1 equal to that. So this is what we're looking for. So which means, what is the takeaway? What is the takeaway now? Okay, the takeaway now is just like, okay, if x1 is Poisson, x2 is Poisson, the sum of x1 and x2 is basically just going to be the sum of the mean, mu1, mu2. And that is what you're seeing here. You see that? That is the sum of the mu. Look at that. You see that? You see that? Which is that? And the Poisson distribution as the mean of mu1, and the other one as a x2 as a mean of mu2. Then the addition of that is basically going to have the addition of the mean. Okay, we're done now. Okay, now I want to go into continuous. Okay, how do we apply the method of transformation with continuous random variable? Okay, now I've just walked you through the discrete, in the discrete example, I walk you through what I call 1-to-1 and 2-to-2. Okay, now I want to visit the continuous random variable now. Okay, the f of x is actually given as this guy. Okay, this is your f of x, right? And this is continuous. And they want you to seek, we're seeking to get the distribution for y. Okay, oh my God, you want to use the method of transformation. Anytime you want to use the method of transformation, whether discrete or continuous, you basically need the inverse. Inverse of this is this guy now. Okay, the inverse is more or less like, okay, get the old variable in terms of the new variable. Now, whenever you are working with the continuous and you are using the method of transformation, you need the Jacobian. Okay, the Jacobian is actually this. You know what Jacobian is going to do now? It's just going to be the x, the y. Okay, you don't need Jacobian in discrete. When we were doing the discrete the other time for method of transformation, we did not need Jacobian transformation. We didn't need Jacobian. But in the case of continuous, whether for one variable or two variable or multi-variable, you basically need Jacobian. Okay, we need Jacobian now, the x, the y, that's 1/2, right? Okay, now in the end, what we basically are gonna do by the time we come back here into the or f of x/12, if I plug in x, and I plug in x, it's gonna be this guy, right? Which is what I'm plugging in here. Look at that now. Okay, that is displacing that x that was initially here. okay, then multiply by the Jacobian. Okay, the Jacobian now, Jacobian J, it has to be absolute in absolute value. I think I made a mistake. I was supposed to put my Jacobian supposed to be absolute in absolute value. We don't want a negative. It's always going to be a positive. Okay. And in the end, this is what I got when I simplify. And I also don't forget, I also need to figure out using this, okay, on this, I need to figure out, okay, the support of y right across the space. Okay, all what I'm just going to do is to put the minimum 1 here. When I plug in 1 here, that's going to be -1, right? And when I plug in 5, okay, what is 2 times 5? 10. 10 minus 3 is 7. Okay, now I'm done. Any question? Any question on how the transformation work, with method of transformation work with a continuous for one variable? Is there any question? Okay. In the absence of question, of course, I'm going to move to multivariable situation now. The multivariable situation, when we have continuous. Okay, maybe you have a joint f of x1, x2 up to whatever. And of course, you need the inverses, okay? Depending on the numbers of variables, you're going to need the inverses, okay? And when you need it, after getting the inverses, we need to set up, when you have one variable, it's just the Jacobian is going to be the x, the y. But when you have more than one variable, the Jacobian is going to be a 2 by 2 matrices. If you have a 3 variables, your Jacobian is going to be 3 by 3. Okay. Okay. Take note of all of that. Okay. So, I just need you to understand, that. Okay. What I'm going to do now, I'm basically going to move. Okay. Let's come to this guy now. Okay. So when you take a look at it, if both X and Y are distributed independently, okay, and they all follow, exponential distribution with mean parameter 1, find the distribution of u plus y, and v equal x over x plus y. Okay, I'm going to leave this for you as an exercise, very, very easy, but you know what? I'm going to do the rigorous one. Okay, I'm going to do the rigorous one. Now, like here now, you know what to do for discrete. This is easy. Okay, discrete, I just put a lot of exercise here. And of course, you know what to do here for continuous for one variable. Okay, for one variable, you know what to do here. Okay, for one variable, for first equal to that, you are seeking to get a distribution of y. Okay, you first need to solve for x. Okay, you get the inverse. Okay, when you get the inverse, you get Jacobian, and we get the Jacobian, then you plug in the inverse into this and you multiply by the Jacobian, you're going to get days. And of course, you can use that to figure out the probability of something less than $500. If you want to do y less than $500, don't forget, this is 500 divided by 1,000, which is going to be, you want to find the probability of y less than 0.1 using the state space of that. Okay, this is a business example application. This is a medical application. Okay, this is a medical application. Okay, so the hospital period in days for patient following treatment for a certain type of kidney disorder is a random variable. Okay, this where S has a density function. Okay, find the probability distribution of y. Okay, you use the method of Jacobian transformation here. You need to first get the inverse. Okay, which is getting x equal to y minus 4. Then you do the Jacobian, there's y. Then you're going to plug in the inverse into this, and you multiply by the Jacobian, then you're going to get the f of y. Okay, the moment you get the f of y, of course, you can now use the new distribution to figure out the probability that, okay, the patient that the hospital period for a patient following this treatment will exceed 8 days. Okay, so this is medical application that I talked about the other time. I have already told you we don't do what we do. There's a reason why we do what we do. If they don't have application in real life, what is the essence of doing them? What is the essence? So they have real life application. That is why we are spending our time on that. Now, this is application, if you take a look at this guy now, okay, it's application in physics and engineering. I know some of you are familiar with the currents and their resistance. Okay, so if the currents actually have a probability distribution and the resistance has the probability distribution, and we want to define a new variable called power, and this power is a combination of currents and resistance. Okay, this is going to be an example of a two by two to two variable, and you need to create an artificial variable here. Okay, the artificial variable that is going to be that's going to be R. Okay, and we basically going to set up Jacobian matrix. But I first wanted to see an example of this before I now use my whiteboard. Okay, now since you've all seen all of that, now I'm actually, what I'm going to do at this time is basically to walk you through the Jacobian transformation for two variable situation in continuous. I'm actually going to stop my, I'm going to stop my share now so that I will be able to, so that I'll be able to make use of my whiteboard. Give me 1 second. Okay, so let me see. I want to make use of my whiteboard. And now, in making use of my whiteboard, what I just want to show you is, a very good example of that is what we call continuous, the T distribution. Okay, T distribution. Oh, I think I've already made a video for T distribution and I'm going to share. It's on YouTube. I'm going to do that of the F distribution. Okay, because of my time. Now, I want to believe, how many of you have heard about F distribution before? If you have heard about F distribution before, can you signify by giving a thumbs up, or you say, yeah, okay, thank you so much. Thank you so much. Now, let me tell you this. F distribution is a distribution that we actually use to figure out p-value if you are conducting analysis of variance test. Maybe you want to compare or means in more than two groups. Okay, you're basically going to use F distribution, but you know what? The F distribution, we derive F distribution, okay, using Jakobia transformation. Now take a look at this. F is a ratio of two independent chi-squared. Okay, U follow chi-squared with arrow 1 degree of freedom. Okay, and V also follow chi-squared with arrow 2 degree of freedom. Okay, now the F of U, okay, is basically U raised to power arrow 1 over 2 minus 1. Okay, exponential raised to power U over 2. Okay, divided by 2 raised to power R1 over 2. Okay, gamma R1 over 2. And as for F of V, okay, is V raised to power R2 over 2 minus 1. Okay, exponential raised to power V over 2. Then we have 2 raised to power R over 2. Then we got gamma R over 2. Now, when you take a look at this, okay, we are U and V are independent chi-squared, okay, and I want to derive F, okay, it means I'm basically need an artificial variable because I cannot go from two variable to one. So I can actually maybe right here, I can create a variable m that is going to be equal to v. Okay, the one in the denominator. Okay. At the end of the day, I'm still going to integrate that guy out, but because I need this guy, because I want to be able to go from 2 to 2. Okay, now take a look at this now. Now, what is the next thing to do? We're told that u and v are independent chi-squared. Okay, since they're independent chi-squared, I'm actually going to say, okay, I need a joint for f of u and v, which is going to be f of u, okay, multiplied by f of v. Okay, I'm actually multiplying this with this. That's what I want to do now. Okay, because the u and v are independent chi-squared. Okay, so if I want to do that now, I'm actually, when you multiply that, so the f of u comma v equal, okay, u r1 over 2 minus 1 v r2 over 2 minus 1 exponential raised to power minus half u plus v. By the time you combine this guy with this guy, all divided by 2 raised to power r1 plus r2 over 2, you're combining this guy with this guy, then we're going to have gamma r1 over 2, then gamma r2 over 2. Take a look at that. That's going to be the joint. Okay? That is basically going to be the joint. That is the first thing you're going to do. You need to get a joint. And the joint is, you're only going to get a joint if you know that the variables involved are independent. All we're just going to do is to multiply the probability or distribution. Okay, that's what led to this. Okay, the next thing is to get the inverses. I want to get the inverses now. Now, we're told that f, give me 1 second. We're told that f equal u equal this. Okay, and we said let m be equal to this. I want to get the inverses. Here, this is more or less like I have r over u1, r2 over v, right? Now, here v is equal to m. Okay, is v equal to m here now? Okay, I want to figure out u here. So u is going to be f r1v over r2. And what is my v equal m? Okay, so what I'm going to do here, so I'm going to say m. Okay, let me rewrite that very well. So this is r1. Now, this is my u, this is my v. So these are the inverses. See the inverses now? That's all what you're going to do for us. That's what you're going to do. You get to the inverses. Okay, so v equal to m now, and u equal to that now. Okay, so you can see u is a function of f and m. You see, it is f, this is m. So u here is a function of f and m, and v is also a function of f and m. There is f here, except that the f is raised to power 0. That's why it's not showing up. Okay, that's why it's not showing up. Okay, now what I'm going to do now is to set up my Jacobian. Okay, because I got 2 inverses. When the inverse is more than 1, you're basically going to have, matrix, Jacobian matrix, which I'm going to show you. I'm going to write now. Okay, so let me clean this guy. Okay, now my Jacobian now is going to be 2 by 2. Okay, I need the u, the f, the u, the m. Okay, and I need the v, the f, and the v, the m. Is there anyone who doesn't understand the formula for the Jacobian matrix? Okay, we're going to differentiate u with respect to f. We're going to differentiate u with respect to m. We're going to differentiate V with respect to F and V with respect to M. Take a look at that. That's all we're going to do. Now, if I basically, here V equal to M, let me write it here. Okay, now let us start doing that. What is the UDF? Okay, you want to do that here. Okay, the UDF is basically going to be R1 over R2M. What is the UDM? F R1 over R2. What is the VDF? Here, the VDF. Okay, the VDF is 0. What is the VDM? 1. Okay, take a look at that. Okay, now if I want to get, this is my Jacobian matrix now. It's my Jacobian matrix now. Now that I have my Jacobian matrix, what am I going to do next? What I'm going to do next is to find the determinant of my Jacobian. In the case of 1-to-1, we don't find the determinant. We just find the absolute value, right, of the Jacobian for 1-to-1. But when you are working with a Jacobian matrix, you're actually going to do the determinant. So what is the determinant now? It's like multiplying that, subtract, in the end, it's just going to be R1, R2, this is my Jacobian. Okay, that's going to be my Jacobian. Okay, now if I have my Jacobian to be that, I got what I need now. The business to go back into the joints of U and V. Okay, when I go into the joint of U and V, I'm actually going to plug in wherever I see U, I'm going to plug in this guy. Wherever I see V, I'm going to plug in this guy. Then I'm going to multiply by the determinant of Jacobian. So let me clean up. I'm going to clean up this guy now. We already have our inverses and we got our Jacobian. Okay, now what we're going to do now, we actually want to get F of, F and M. Okay, the new variable. Okay, if I want to get the F of F and M, the new variable, what I'm actually going to do is more or less like, okay, I'm actually going to express, the inverse of this guy, okay, the inverse of that guy. Okay, I'm talking about the formula now and everything multiplied by the determinant of Jacobian. Okay, that is exactly what I want to do. Okay, I'm actually going to come back now to the join, start plugging in. Okay, so instead of U, it's going to be F, R1, M, okay, over R2, everything raised to power R1 over 2 minus 1. Okay, now instead of V, it's going to be M raised to power R over 2 minus 1. Then exponential raised to power minus R, okay, U plus V. Okay, so the U plus V now is basically, what is my U? So FR1M over R2. Okay, what is my V? Okay, plus M. Okay, let's take a look at that. Okay, now the moment I have that, okay, don't forget, let me clean this so that I can have a space. Now, I'm going to multiply here, okay, by my Jacobian. Let me put my Jacobian here out of this M, right? Okay, so that I can clean up. So when I clean up this guy now, don't forget the denominator. Initially 2 R1 plus R2 over 2, okay, gamma R1 over 2, okay, gamma R2 over 2. Okay, this is what I have now. This is my joint. Okay, the joint for the new variables. When you take a look at this joint now, okay, we basically need to simplify these joints. And after simplifying that, then we're basically going to integrate out M. Don't forget, we're not interested in M. M was the artificial variable. So what I'm going to do, let me clean up. Okay, so I'm going to clean up now. Okay, so it cleaning up now. Okay, the F of F and M, okay, equal. Now you just need some, here, f raised to power r1 over 2 minus 1. Okay, r1, r2 raised to power r1 over 2 minus 1, then m, okay, raised to power r1 over 2 minus 1. I just simplify this guy, okay, and when you combine this with that guy, I'm afraid I'm actually gonna have r2, give me 1 second. I think, by the time I try to put them together, r2 over 2 minus 1, okay, then I'm actually going to have exponential raised to power negative half into, okay. Now, let me, if I bring out m, okay, if I bring out m, let me continue it from here because of my space. So if I bring out m, okay, don't forget there's a 2. I'm basically going to have f of r1 over r2 plus 1, okay. You see that? And don't forget the Jacobian, r1 r2m, okay, and everything here, okay, all divided, okay. Don't forget this guy here. So I'm actually, let me first cancel this guy. Okay, what I'm doing now, just simplifying. So 2 raised to power r1 r2 over 2, okay, gamma r1, then gamma r2 over 2, okay. That's what we got for now. Okay, now this is looking messy, right? We got to simplify all of that. Okay, in the simplification now, okay, f r1 over 2 minus 1, okay, r1 r2, okay. If you take a look at this and this guy, we can combine the two of them, law of indices. That is basically going to be this. Okay, we've already combined that, and we're going to have, now when you take a look at this and take a look at this m, okay, a law of indices, that minus 1 is going to go away, right? We're going to have r1 r2 over 2, okay. When I have that, I don't have all this guy anymore. Basically going to have exponential raised to power m over 2, okay, f of r1 r2 plus 1, okay, everything divided by 2 raised to power r1 r2, okay, divided by 2, okay, gamma r1 over 2, gamma r2 over 2. Now it's no longer looking messy anymore. Now this is what we have for the joint, okay. Now if we have this guy for the joint now, so what are we going to do next? This is what we're going to do next, okay. I'm going to clean up this guy now, okay. Some of you can be taking the picture, okay. That's no problem. I allow that. I'm flexible, okay. Very, very flexible. Okay, so what I'm looking for is f of that, so which is going to be f of this m, right? The m, you forgot that. The m, go from 0 to infinity, right? I want to integrate this guy now. Okay, I want to integrate this guy. So if I have f of f now, okay, put it 0 to infinity, dm. Oh my God, I want to integrate this guy now. I want to integrate the m out. I'm not interested in the m. I told you the other time, was an artificial variable. Okay, so that's what I want to do. So if I want to do that with respect to m now, so I'm first gonna write this out. So with respect to m, okay, so f is gonna be out. That's a constant, right? Okay, r1 over r2 raised to power r1 over 2 is gonna come out. Okay, what about the denominator 1? Okay, gamma r1 over 2, gamma r2 over 2, they're gonna come out. Then I'm now gonna be left with m raised to power r1 plus r2 over 2 exponential raised to power minus m over 2 f of r1 r2 over 2 plus 1. Okay, so the m. Okay, that's what I want to do now. Okay, take a look at that. Mass is easy. Okay, now the moment I have that guy now, I want to be focusing on the one in the integral. I want to focus on the one in the integral. Don't forget, we want to use a gamma function, but before using the gamma function, we first need to use the method of substitution. We can let P to be equal m over 2 f r1 r2 plus 1. Okay, that is going to imply what is going to be my m. Okay, my m is basically going to be 2p. Okay, 2p divided by f of this, right? That's going to be my m, right? So what is going to be the p, the m? Okay, the p, the m is going to be f of r1, r2 plus 1, okay, divided by 2. What is the m? Okay, what is the m now? The m is going to be 2dp, right? 2dp, okay, divided by f of r1, r2 plus 1. I need all this, okay? I need all this, so I'm going to plug them in, okay? Now, if I now come back, let's say I've already done all of that, and I basically want to plug them in, here now, instead of m, okay? Instead of m, if I write 2p raised to power f r1, r2 plus 1, all of that, raised to power that guy, okay? Then the other one here is just going to be raised to power negative p. And instead of the m, what am I going to have? Instead of the m, I'm actually going to have 2 dp divided by f r1, r2 plus 1. That's what I'm going to have. Take a look at what I have now. Okay, it's taking shape. Oh my God, it's taking shape now. Then I'm going to clean up this guy. I'm going to clean up this guy now. Just clean up this guy now. Okay, clean up that guy now. Now, as I clean up now, okay, now don't forget I got this minus 1, r1, r2, r1 over 2, 2 r1 plus r2 over 2, gamma r1 over 2, gamma r2 over 2. Now here, there's a 2. If you take a look at 2 raised to power 1 here, there's another 2 here raised to power that guy, right? Okay, now when you take a look at the 2 raised to power this guy here, and there's another 2 here, okay, we can actually pull them together. So if I write 2 raised to power r1 plus r2, okay, over 2, okay, there's going to be plus 1, okay, and down here this guy and this guy, okay. So by the time you simplify and do what you're supposed to do and use gamma function without wasting time, because I get 2 more minutes, I'm just going to write the final result. Okay, let me clean up. Let me just the final result. You're going to see the final result now. By the time you follow it that way, you follow that way, you use the gamma function in the end. This is what you're going to have. The distribution now, okay, is basically going to be this r1 over 2 minus 1, r1 over this raised to power r1 over 2 divided by b of r1 over 2, r2 over 2, okay, then 1 plus r1 over r2 f all raised to power negative into r1 plus r2 over 2. This is what you're going to have at the end of the day. This is what we call the F distribution. And don't forget, the guy in the denominator, the guy in the denominator, the non-integral derivation, don't forget, is this guy here, right? divided by R1 plus R2 over 2. Okay, so that is how we derive the F distribution that we use to figure out p-value if you want to take a decision when you run the analysis of variance test. You can see without mathematical knowledge, there's no way we will be able to have some statistical technique that we use on data in place. We're not going to have them. And that's why the theory of statistics is very, very essential. So why is it that we still study theory of statistics up to today? We still study this because, don't forget things we like, things are changing, right? We may want to be able to modify, modify our, what is it called? We want to modify our model to commiserate with reality. Things are changing. I remember what I did in my PhD work in 2016 that I presented at the University of Oxford in the United Kingdom. Okay, I actually, develop a brand new distribution that we call exponentiated F distribution. Okay, that is published. You can check online. If you Google my name on the Google Scholar, you're going to see what I work on. So why is it that I have to produce a the brand new distribution is because if you want to conduct analysis of variance tests, we have assumptions of normality and so on like that. What if the assumption is violated? If the assumptions are violated, you cannot use F test anymore. We can't do that in the jurisdiction of F distribution anymore. And what did I do? Okay, instead of, also, scientists, they are researchers, when there's a violation like that, they normally resolve into what I call non-parametric approach. That is very, very weak. I don't know whether you guys have heard about Kuskawali's test. The Kuskawali's test is very, very weak. It's measured on a weaker scale. And what did I do? What I did with my PhD work was, okay, you know what? Since I understand the derivation of F distribution and the F distribution is having a problem, can I have a way to incorporate skewness parameter into F distribution? Because my data set is skewed. I want to make my distribution to be skewed. That was what I did. And that's, the problem I faced was mathematical complexity, but that was a breakthrough at the end of the day. Okay, this is where I'm actually going to stop today, and I'm going to return to in person on Monday. That on Monday, we're going to talk about other statistics, which is the last, subtopic. Okay, last Monday is going to be the last day. So after Monday, on Tuesday, I'm just going to walk you through practice questions, the final practice questions. And don't forget, I told you, the final exam is going to be cumulative. Okay, chapter 2, chapter 3, chapter 4, 5, and 6. There's not going to be chapter 1. I told you, chapter 1 is too elementary. This week, before the end of the week, you're basically going to see final exam practice questions. Is there anyone want to ask question before I go today? Is there anyone? Is there anyone want to ask question before I go today? Okay, in the absence of that, make sure you all stay safe. See you in person on Monday. Bye for now, everyone.
Thank you.
You're welcome.
Take care.
You're welcome.